Good day everybody, Mr. Bailey here, and my mission is to prove to you where the product rule comes from and that it does make sense in case you've been taught it in a fairly quick way, which I've been guilty of in the past and sometimes maybe will in the future, depending on time restraints. Sometimes a product rule is just dropped into your laps from thin air. Here it is, trust it works. But I think it's always good to try and show where these things come from. So I'm going to prove to you where it comes from, why it works, using the first principles you've seen from year 12. So, before we do that though, I do need to just mention a little thing about this proof. A special note, if you will. And this special note, before we begin with the proof, what we need to do is use a general result, which I won't robustly prove here. You might see this proof more robust in a university course or something like this, for example, or you can search online. But I'm just going to fairly informally explain the leap of faith we're making here, but also that this leap of faith is reasonable. So this is the leap of faith we need to be making. If f of x and g of x are both differentiable functions, functions that can be differentiated, with a limit that exists as h approaches 0, then what we can say is the limit of h approaching 0 of the function f of x and added to the derivative function of g of x is the same as the limit of h approaching 0 of f of x is derivative separately added to g of h's derivative. So essentially we're saying what we can do here is we can split the limit into two. So the limit of f of x plus g of x, the derivative function of both combined, is the same as the derivative function of those taken separately and then added together afterwards. So just to illustrate what I mean, I'm going to take an example for f of x being 2x and g of x being x squared, and just showing that this point does hold up and is true. So, for h going towards 0, the derivative from first principles of f of x plus g of x is this here. So as h approaches 0, if we input f of x being 2x, so f of x plus h becomes 2 lots of x plus h minus 2x. And similarly, for g of x, if we input x squared, so if we input x into this, then we're going to square the input. So g of x plus h becomes x plus h squared minus x squared all over h. So carrying this through, expanding the brackets, we get this. As you can see here, these two x's cancel those two x's, x squared cancels with this x squared. We then get this. The h's will cancel on the numerator and denominator here, just leaving us with 2, and over here similarly will give us the limit of h approaches 0 of 2 plus 2x plus h. As h approaches 0, we just get that this limit is 2 plus 2x. So taking these limits together as one, we get the limit of f of x plus g of x all over h as the derivative functions of both combined as one is 2 plus 2x. Doing these derivative functions separately though, and computing them separately then adding together, what would we get? So in red, I'm just going to box this off. This is given us 2 plus 2x, but what if we were to just take the derivative function of f of x? Well, this would be 2x plus 2h minus 2x all over h, which when simplified is 2h over h, which is just obviously 2. And so this limit, taken separately, just gives us 2. What about the derivative function g of x on its own? Well, the derivative of g of x would become x plus h all squared minus x squared over h, which expanded out gives us this. The x squareds will cancel, giving us this line. The h's will cancel to give us the limit of h, as h approaches 0, of 2x plus h, which of course, as h vanishes to 0, is just 2x. And so this limit in green is just 2x. So therefore we can see this limit in blue plus this limit in green gives us 2 plus 2x, which is the same as the initial limit over here in red. So therefore, to conclude, the derivative function of two functions combined as one limit is the same as the derivative functions of those functions taken separately and then added together. Long story cut short, we can split the limit into two pieces. Now we've established that, we can get on with the proof proper. So recall from year 12, the definition of the derivative of a function y, where y is f of x with respect to x. This is the derivative function. So we're going to use this throughout. So now let's introduce two new functions of x, call them u of x and v of x. Then in exactly the same way as we had f dashed of x for dy by dx, then u dashed of x is du by dx, which is this beast here, and v dashed x in the same way over there. Now, again, let's just imagine that y is a product of two other functions, so that y is big F of x, where big F is the product of functions u and v. Then the derivative of big F of x, f dashed of x, is this using the year 12 definition of the derivative. However, f of x plus h is going to be u of x plus h multiplied by v of x plus h, minus f of x, which is minus the product of u and v, all over h. So where do we go now? Well, what we're going to do is we're going to tactically add and subtract u of x plus h and v of x. And this is a moment of genius. It's why would you think to do that? Well, it makes sense after the fact, but knowing to do that beforehand, it must have just been a very genius insight that somebody made. Anyway, so now we have u x plus h v x plus h minus the u x plus h v of x we created, plus it here, so this bit will cancel to 0, minus u of x v of x all over h. So why did we do that? Well, now we've got 4 bits on the numerator, so these first two parts will factorise out all over h, and we can factorise these 2 bits all out all over h to give us this next line. So this first 2 pieces, we can factorise out the u x plus h to give us this. And the second part, we can factorise out to give this. So all we've done here, factorise out the u x plus h. This bit we've put here, all over h. And then this part, we factored out the v of x, and what v of x has been multiplied by, which is this and that, we've put over here and separate out the fraction. In fact, just to be a bit clearer, what we did here with the ux plus h, what we were multiplying it by was the vx plus h and the v of x minus v of x, which makes this numerator here. So the next step, what we can do, is separate out these limits, and that's okay because we talked about that in the special note. We can split the limit into 2. The limit of this thing plus this one is the same as the limit of one plus the limit of the other taken separately. Now as h shrinks towards 0, u of x plus h will just become u of x, and v of x is just v of x and does not depend on h at all. So what we can do here, we can move the v of x and the u of x, which now will essentially not depend on h. We can move these outside of the limit and treat them as almost like a constant which has nothing to do with h. So if I move the u of x and this v of x on the outside of these brackets, we now get this. And now if we compare what's in the red and what's in the blue here to how we defined the definition of the derivative from year 12, we can see here that this in the blue is the definition of the derivative of v of x, this is v dashed of x, and this in red is u dashed of x. So replacing this with what these actually are, this is u of x times v dashed of x plus vx multiplied by u dashed of x, which is the product rule. So if you differentiate f dashed of x, we keep the function u the same, differentiate v, multiply them together, and then we leave the final function the same and multiply it by the derivative of the first function. So that is the product rule, which is stated here. So that's a fairly common textbook way you'll see the product rule stated, but there's a few different ways you may see it written, which I'm going to talk through here. There's 3 main ways in my head. So, the textbook way, in other notation, in dy by dx notation, if y is uv, then dy by dx is u dv by dx plus v du by dx, or in absolute shorthand, which is how I was taught back at King's School, Macclesfield, uv all dashed is u dashed v plus v dashed u. So those are the notations you might want to make a note of they are useful in your studies. And that's all from me essentially. So let the screen go to black, a bit spooky, and then fade to white. And a big, genuine thank you for me for watching the video, and as ever, I do hope you found some of it at least very useful. So take care until next time, and tune in again for the next one. So from Mr. Bailey, goodbye from now.